Look up at the sky when the sun is down. What do you see? Black mostly, right? You see a few thousand scattered stars, maybe the ghostly band of the Milky Way if you're far from city lights, but mostly it's just black emptiness. That seems normal. But stop and think about it for a second, because if the universe is truly infinite or even just unbelievably massive and old, that view should be impossible. The night sky should be blindingly bright. That confusion is one of the oldest mysteries in science. It is a simple question that philosophers and astronomers wrestled with for hundreds of years, and finding the answer completely changed how we understand the cosmos. This problem asks, if you live in a place full of sources of light, stars, and galaxies, why is the sky so dark? Imagine you are standing in the middle of a huge, ancient forest. If the forest goes on forever, no matter which way you look, your line of sight should eventually land on a tree trunk. If the universe is like that, if stars stretch out infinitely in every direction, then every single patch of sky, no matter how small, should have a star sitting on it. You should be staring directly at the surface of a star. Now you might think, but stars are really far away, so they look dimmer. That is true. A single star twice as far away looks a quarter as bright. But here is the critical twist that makes the problem so sticky. In an infinite universe, every time you double your distance, you also find 4 times as many stars. Think of space as being filled evenly with shining objects. As you look farther out, you're looking through a thicker shell of stars. The increase in the number of stars perfectly cancels out the decrease in brightness caused by the distance. The math works out like this. The light coming from a nearby star fades quickly, but the enormous volume of space added by looking just a little farther away ensures that the combined light from all those new far-off stars exactly makes up the difference. If the universe extended forever, filled with shining stars, every line of sight would terminate on a star's surface. The entire night sky should be uniformly bright, hotter than the surface of the sun, making Earth uninhabitable. This puzzle haunted thinkers for centuries. It suggests that one of our fundamental assumptions about the universe must be incorrect. Is the universe truly infinite? Are stars truly eternal? Or is the darkness telling us something important about the history of space and time itself? We know that every star you can see with your eye is part of our home, the Milky Way galaxy. But that is only a tiny portion of the universe, which contains an estimated 100 billion galaxies. Between these gigantic structures, space is largely empty, containing only thin gas. The light from those countless stars is out there, moving toward us, but something prevents it from reaching us in a way that blinds us. To truly appreciate the mystery of the dark night sky, let's imagine what the world would look like if the intuitive, simple version of the universe, the infinite and eternal version, were true. If the cosmos stretched forever and had existed forever, the entire celestial sphere would be a wall of searing light. In this imaginary universe, time itself has no beginning or end. Stars form, live their lives, and never burn out. Energy is constant, and the density of shining objects is always the same everywhere you look. In this model, every point in the night sky must correspond to the surface of a star, no matter how distant that star is. There would be no dark patches. Think about standing inside a colossal oven. Everything around you would be radiating energy. On Earth, we are constantly bombarded by a thin trickle of solar radiation, which gives us heat and light. In this eternal, infinite cosmos, that radiation would come from every direction, all the time. Since every line of sight eventually hits a star, the combined heat and light from all those stellar surfaces would heat the entire planet to the average temperature of a star's surface, roughly 6,000 degrees. The very idea of night would cease to exist. Our planet would be perpetually bathed in light brighter than the sun. The intense heat would prevent the formation of liquid water, boiling oceans into vapor instantly. Life, as we know it, would be impossible. All matter, including the Earth, would eventually vaporize or reach thermal equilibrium with the surrounding stellar radiation, turning the whole cosmos into a glowing fog. But we look up, and the sky is black. The fact that we have night at all, the simple, quiet darkness you see when the sun sets, proves that the universe is not the infinite, unchanging place many early thinkers assumed it must be. The presence of that darkness is the most powerful piece of observational evidence we have against the model of an eternal, static cosmos. So where is all the missing light? Why are those countless star surfaces not visible? The two main answers that resolve this paradox both have to do with time, the time light takes to travel, and the age of the universe itself. The distances in space are staggering. Our local galaxy, the Milky Way, contains hundreds of billions of stars. Yet even stars within the Milky Way are separated by enormous distances. Outside the galaxy, the space between the hundreds of billions of galaxies believed to be in the cosmos is so vast that light takes millions or billions of years to cross them. The solution to the dark night sky problem hinges on the fundamental speed limit of the universe, the speed of light. Because light travels at a fixed, finite speed, the universe cannot communicate instantly across those vast distances. We see objects not as they are now, but as they were when the light began its journey toward us. This realization is the key to proving that the universe is neither infinite nor eternal in the way that would create a searingly bright night sky. The universe doesn't look like a solid wall of star surfaces for two primary reasons related to time. The first reason is that the universe has a beginning and is not infinitely old. The second related reason is that light travels at a finite speed. If the universe were infinitely old, the light from those most distant, ancient stars would have had plenty of time to reach us. But the universe is only 13.7 billion years old. It originated in the Big Bang. This means that we can only see objects whose light has had enough time to travel across space and reach our telescopes since that beginning moment. Think of it this way. There is a huge sphere around us called the observable universe. The radius of this sphere is limited by the age of the universe. We cannot receive light from anything outside that boundary because that light started its journey toward us before we existed, or before the cosmos was structured enough for light to travel freely. This immediately solves half of the paradox. Since the universe has a finite age, the light has not had time to reach us from objects far enough away to fill in the dark gaps in the sky. The oldest observable light we can see comes from the period when the universe was only about 380,000 years old. Before that time, the universe was so hot and dense that light waves could not propagate freely. They were trapped, constantly scattering and being absorbed by matter. The discovery of the cosmic microwave background, CMB radiation, thermal microwave radiation, left over from the Big Bang confirms this finite beginning. This light is the farthest back we can look using normal electromagnetic waves, and it is the edge of our visible cosmos. We can look to this wall of light in every direction, but since it is very faint microwave radiation, it certainly doesn't light up the night sky like a star surface. The second part of the answer lies in the huge distances between galaxies. Astronomers generally think of a galaxy as an island universe, a system of stars, dust, gas, and dark matter held together by gravity. Our Milky Way is big, spanning about 100,000 light-years across. But even at that size, it is separated from its nearest major neighbor, the Andromeda Galaxy, by 2.5 million light-years. When we look into the dark sky, we are looking through the void, the truly empty space between galaxies. Even though there are billions of galaxies out there, they are spread so far apart across the immense volume of space that the space between them appears dark. If you took all the stars and distributed them evenly across the entire volume of the universe, their total density would be incredibly thin. So, the sky is dark because the universe is not eternal, it has a beginning that limits how far back in time we can see. And the energy coming from the visible sources is spread out over enormous, mostly empty volumes of space. If you could travel out 10 billion light-years, look around and come right back, you would realize that most of the light we should be seeing simply hasn't reached us yet. The ultimate solution to the dark night sky isn't just about the age of the universe. It is also profoundly linked to the continuous expansion of space and the fixed speed of light. This combination introduces an extra factor that diminishes the energy of light from distant objects, redshift. Because light travels at a fixed, finite speed, looking out into space is literally looking back into the past. Light from distant galaxies takes billions of years to reach us, acting as an automatic time machine. As the universe expands, the fabric of space itself stretches. When light travels through this expanding space, the distance it covers increases, and its wavelength gets stretched out, like butter being spread across more bread. As the wavelength stretches, the light becomes redder, a phenomenon called cosmological redshift. Crucially, as the wavelength stretches, the light loses energy. For objects that are relatively close, say within a billion light-years, the expansion doesn't make a huge difference in brightness. But for the most distant galaxies, those billions of light-years away, redshift is powerful. The light from these ancient sources is stretched so dramatically that its energy is severely diminished by the time it reaches us. Imagine light emitted by a star in the visible spectrum, the colors our eyes can see. By the time that light has traveled across the expanding cosmos for billions of years, its wavelength might be stretched so far that it is no longer visible to our eyes. It may have been pushed completely into the infrared or even radio wavelengths. In this way, the expansion of space steals the light's energy, converting the fierce visible light into faint, harmless, long wavelength radiation. This process reinforces the darkness of the night sky in two ways. First, the fixed speed of light limits the maximum distance, and therefore age, of the objects we can see. Second, the expansion of space redshift stretches the energy out of the light from those most distant objects. This redshift effect is the reason astronomers use instruments like the James Webb Space Telescope, JWST. JWST is designed to see the universe in infrared light. Many of the first galaxies that JWST images are technically visible to us, but their light is so heavily redshifted by the expansion of space that they shine most brightly in the infrared spectrum by the time their light reaches us. An image like the Hubble Deep Field taken in visible light shows the ancient universe populated by puny, seemingly unremarkable galaxies. But when we look at the same patch of sky in infrared, those blurry, visible light objects can sometimes correspond to incredibly energetic, dusty, star-forming galaxies that were previously invisible. This powerful, invisible light confirms that the energy is there, but the stretching of space has moved it out of the visible range. If the universe were static, this wouldn't happen. If light didn't have a fixed speed, there would be no time delay, and the paradox would return. But because of the fundamental nature of light's speed and the continuous fixed expansion of space, the distant stars cannot overcome the twin cosmic hurdles of limited age and energy dilution. The darkness of the night sky is the simplest, most profound evidence we have that the universe began with the Big Bang. If the cosmos were infinite and eternal, the sky would glow white hot, but since it is dark, we know that the light we expected is missing. The fact that the light is missing is direct evidence that the cosmos has a finite history, a starting point roughly 13.8 billion years ago. The ability to look backward in time thanks to the finite speed of light allows us to study the baby universe. When astronomers observe extremely distant quasars, active galactic nuclei powered by supermassive black holes, they are seeing light that has traveled for billions of years. For instance, light from one quasar, 3C273, was found to have traveled for about 2 billion years to reach us. This confirms that the universe has evolved over time. These ancient active black holes were 100 times more common 10 billion years ago than they are today. This pattern of declining activity confirms that conditions have changed significantly since the beginning. The light that has traveled the farthest to reach us is the cosmic microwave background, CMB radiation. This is the leftover energy from the Big Bang. This light confirms that the universe was once uniform, hot, and dense. It confirms that we live in a universe that has a history. The light we see today from the CMB began traveling when the universe was only 380,000 years old, as before that point, the high temperature and density meant photons were trapped by matter. Furthermore, the expansion of the universe, confirmed by the redshift of distant galaxies, tells us that the universe is not static. The rapid expansion in the early phases of the universe, called inflation, amplified quantum mechanical fluctuations to produce the seed structures that eventually grew into the immense structures we see today. This initial condition, an incredibly hot, compressed starting point followed by rapid expansion, is the story confirmed by the very darkness of the night sky. The light that was created has not yet reached every corner of the vast space created by that expansion. The fact that the night sky is black is not a sign of emptiness, but a sign of cosmic youth and motion. The darkness proves that time and space are not infinite, eternal entities, but rather elements that are changing and expanding. Every time you look up and see the dark void, you are seeing a direct consequence of the Big Bang, the age of the universe, and the constant speed of light. We started with a simple question: why is the night sky dark? The simple question led us through centuries of confusion until modern cosmology provided a complex yet satisfying answer. The answer is that the universe is not the ancient, infinite, and unchanging place that would guarantee a blinding sky. Instead, the universe is governed by three primary principles that guarantee the darkness. First, the universe has a finite age of roughly 13.8 billion years. This means that light from objects farther away than the observable limit, light that would otherwise fill the dark gaps, simply has not had enough time to reach us. Second, light travels at a fixed, finite speed. This constant velocity, which cannot be exceeded, imposes a fundamental time delay on every piece of information we receive from space. This finite speed is what turns our telescopes into time machines, allowing us to peer back to the universe's earliest days. Third, the universe is continuously expanding. This expansion stretches the wavelength of light over immense cosmic distances, causing cosmological redshift. This stretching diminishes the light's energy, transforming bright, visible starlight into faint, long wavelength radiation by the time it finally arrives here. These three rules work together to solve the paradox completely. The darkness of the night sky isn't a flaw, it is a signature. It confirms that the basic assumptions of the infinite, static cosmos are entirely incorrect. The simple visual of a few scattered stars against a field of black proves that the universe is dynamic, structured, and has a measurable beginning. If you want to understand space like a NASA-level analyst quick without studying for years or paying thousands for a university degree, we have a free community that will help you. Link is below. The mystery of the dark night sky confirms the Big Bang theory and sets the stage for everything we observe in modern astronomy, from the formation of galaxies to the evolution of supermassive black holes. When you look up and see the quiet blackness, you are seeing the shadow of cosmic history, the absence of light that is either still traveling toward us or whose energy has been diluted by time and distance. The darkness is the most profound proof that we live in a universe defined by change and time. If you want to understand the fixed, absolute speed that governs everything in the cosmos, including how quickly we can look into the past and why the expansion of space is the biggest challenge to galactic communication, click here to Why Light Has a Speed Limit video.